Okay, so I should have passed out to you. You have a purple packet there. It's on waves. It's our last unit for the course. And then I also handed out to you that exam review. Again, exam review is not a requirement to do, just good to do. Well, I should take a moment on the back side of that exam review, if you would, just take a look at that. You are allowed a 3x5 index card, both sides. So anything you'd like to be able to bring in, you can in preparation for that exam. Okay, our last topic is on waves. It's our last unit. And so you'll see in that exam review, the last page or two is reserved for wave-related stuff. Wave terminology, wave properties, waves and technology is what this is going to be about. This is not the same as your math classes where you learn how to do sines and cosine graphs and things like that. This is more about physical waves. And so I do want to take a moment and talk about this image search that I did. In fact, this is probably about 2-3 years ago when I first started putting this slide together. And I did a search for information age, which is the age that we currently live in. And so this is one of the key pictures that came back, was a bunch of communication related equipment up there. And so maybe a news broadcaster there. You have a variety of different things there that are all about information. Now, some of you have heard of this thing called analog versus digital. If you haven't, analog signals are continuous signals, sort of like a ramp that is just a continuous elevation change from the ground up to the very top. Well, most of our information today is sent digitally, which means that it just comes in discrete steps, mostly zeros and ones. And so we can get to the top of that staircase either using a continuous ramp or a digital kind of setting. There's a whole lot of advantages to using digital communication, and I'm hoping that by the time we're done with this unit, you understand what some of those advantages are. Make sure your name is on that front page, just in case you leave it here. And then I want to take a little bit of time to talk about the WAVE research project. This project is not a build project like you guys have done in the past. You guys built your egg drop, you built your mechanical launcher, then you built your speakers. By the way, I'm going to get rid of those speakers. You guys have your pictures, I assume, for those things. Maybe not. Okay, so I won't get rid of those just yet. But again, make sure you get those things all done. Are you going to finish that up during Academy today? Is that what the plan is? Okay. But then I want to get rid of those speakers. The WAVE research project is, it's more of, just as it sounds, it's a research that you do related to some piece of technology, and you can see there's probably about 40 or so different things up there to choose from. If something else seems interesting to you and you can just share that with me and what you think might be interesting for you to look at, that'd be fine. Just talk with me on it. So on this list of 40-ish or so things, you'll see things like laser surgery, MRIs, X-rays, fiber optics for transmitting versus with light, fingerprinting, you got holograms, you've got NASA rover capabilities, shockwave therapy. There's a tremendous number of things that you could look at. The goal here is that you would do some research on a project, on a topic, and then this one you'd actually present to your classmates. So as opposed to the others where you've just created a series of slides, this one you'd do a presentation on. And so there's more stuff that we can cover in this unit, and so we want you to sort of be the teacher for one of your topics. The idea behind the presentation is that you would just do some research on the history of the device. How it works would be the main physics portion that I'd be looking at. Emphasize wave-related phenomena, so we'll look at some different wave properties and wave phenomena that you can emphasize for this. Applications, and then what's on the horizon. Most of the technology here has been around for a while, except for some of the more recent things like holograms and quantum cryptography and things like that. Those are a little bit newer, but what's on the horizon, so how are these things evolving, if you will, as time goes on. I'm going to have you guys choose a topic. I think Wednesday is the day that I'm going to have you guys choose. It's early in the unit, and the reason for that is Friday I'm planning to be gone, and I'm going to have Friday be your first research day, so you can start into some of the things about history of the device and maybe some applications, what's on the horizon. How it works, the wave-related phenomena stuff that I'm going to spend the next week or two try to talk through with you, so you can at least start on Friday doing some of the initial research. Okay, questions for me on that project? Okay, that's our end of unit test, if you will. All right, I want to do some things with you guys today on just properties of waves, at least starting into this discussion. A wave is simply the motion of a periodic disturbance. So when we create a disturbance, we can allow that disturbance to propagate. I've had this slinky up here my entire time that I've been teaching here at the school, and this is a great way of demonstrating how we can transmit a wave as a disturbance. So when I use my hand to create some sort of disturbance there, it's able to propagate through that medium. What allows that to propagate is internal forces. So we started the course with talking about how forces can cause changes in motion. We need to have some sort of connecting force between elements that make up that slinky. Internal forces within the medium allow the energy to travel. And so what these things are called, it's called energy waves. So I'm really not moving an object from left to right. What I'm doing is I'm just allowing that disturbance to propagate. So you've probably seen water waves. You drop something into, drop a stone into the water there, and you can see some circular waves propagate. Any of you ever been a part of a person wave, maybe at a stadium where you see people do this kind of thing? Anyone ever do that? We're going to try that right now. Okay, so we're going to have you guys start this, and so you guys are going to create the disturbance. It's going to be sending through this group over here, and then Liam is going to be the last person and Abby to do this. Are you guys ready? Okay, you guys start it. Go. And then it goes over there. And it looks like the Liam, how you doing over there? You missed the. Let's try that again. All right, are you guys ready? Okay, go. All right, Liam and Abby, you guys start it.
What?
Yeah, we're doing a wave here, Liam. Come on, help me out now. Ready? 3, 2, 1, go. It's the saddest looking wave I think I've ever seen. All right. We're sending the disturbance along through the medium. You guys are properties of that medium. Oh my gosh. Liam. All right. Disturbance travels in a straight line while the particles simply oscillate, except for Liam. So they oscillate about in equilibrium position. This motion is described as simple harmonic. Now there's an asterisk next to that, and I want to take a moment and tell you what that asterisk means. Down at the very bottom, it says project, but not on the quiz or exam. So you'll see a variety of topics that are presented, that I present in these lectures, that are just not necessarily for enrichment, but they're not going to be part of a quiz or an exam. They are probably going to be a part of someone's project. So I'll go through those with you just so you understand what's going on with those, but you would not see those on a quiz or an exam. Now, waves require no bulk transfer of matter, so we're not moving matter from point A to point B. Energy, therefore, is able to transmit very efficiently. We can send it extremely large distances with very minimal energy needs. So waves, again, allow us to send energy without sending matter. Okay, so it's very efficient. All right. Now, I have a simulation up here that I'm going to have us spend some time looking at. This one here is a site that I reference oftentimes from Dr. Daniel Russell. He's currently a professor of acoustics at Penn State, and so I've been following his site for a long time. This site has a tremendous number of things for us to look at, animations to help us understand waveforms. First, I'm just going to show you what is a wave. This is what I was attempting to do with you guys, and it worked pretty well for the most part. So you notice on the left-hand side, the person starts the propagation, and then it transmits through the people of that medium. Now here we see what's called a pulse wave. So the red bar is initiating the motion, and then I'm able to send that disturbance through the medium, which in this case is just a series of particles. And you can clearly see that the energy is what's transmitting from the left to the right, even though the particles themselves don't really move anywhere. Now, you could draw a pulse wave as something that looks like this here, or you could draw it something like the red bar transmitting the energy through those mediums. If I have a continuous wave, the continuous wave, the thing on the bottom right, is much more of what we mean by a continuous wave transmitting energy. So on the left-hand side, outside of the view of that simulation, there's some disturbance. It's producing some sort of transfer of energy from the left to the right. You can see the particles themselves that are highlighted in red just oscillate, whereas the energy sort of flows through it. So we can talk about the motion of the particle in relation to the motion of the wave. So the wave is traveling from left to right, even though the particles don't, in the big scheme of things, go anywhere. And so again, waves are able to transmit energy without moving matter from left to right. Now on this simulation, there's a whole host of things that you could look at, and I want to give you guys some time to be able to look at some of these things. So again, this is what is a wave. We can do some other things here, talking about refraction of sound waves. Some of you might have heard of the Doppler effect. You could look at that link if you'd like to. I want to move into some of these other things over here. Vibrating objects, things like waves and so forth, are an important part of everyday life. I want to show you guys some things here. Here's let's do this one, rectangular membrane. So if you play a drum or anything like that, you might strike that drum skin, and you can see that it produces some sort of sound vibrating in different modes. So these different modes of vibration would lead to different kinds of sound. And so you could have a mode of vibration that looks like this. It could look like a trampoline surface, if you will, that's just sort of vibrating up and down. Sometimes you can have that trampoline surface vibrating sort of like this. It could vibrate in a variety of different modes. And so all these different modes of vibration would lead to different kinds of oscillatory motion. So you can get some pretty complex waveforms there. Now, unfortunately, the mathematics can get quite involved. And so again, in order for you to be able to go through and do the mathematics of this would require calculus and so forth. So we wouldn't get into the math for that. But let me take a look at let's take a look at a rectangular beam. So if you've ever seen the Tacoma Narrows Bridge that was oscillating due to wind, I'll show you that video in another week or so when we look at resonance. Objects like, in this case, could be a steel beam, can vibrate in a variety of patterns as well. And so you can see these kinds of vibrational patterns that look like so. And so objects that have that are made up of molecules, if you will, can vibrate in a variety of different ways. Now, the one that I found sort of interesting, and I know we have some hockey players in here, I want to show you the vibrational modes of a hockey stick. And so I would imagine, Ryder, can I pick on you for a minute? Yeah. If you, I know you're more defense, yeah, right? But you still obviously have to hit the puck from time to time, right? Yeah. When you hit the puck with your stick, does it ever vibrate sort of erratically in your hand at all? Probably not, because you're pretty good at hitting that puck, right? But if you look at the vibrational modes of a hockey stick, when you hit a puck, sometimes you hit that puck in a weird spot that starts to cause some vibrations in the hockey stick. Now you also play baseball, right? So same idea for a baseball bat, and I don't think I have one here right now, but same idea. When you hit, sometimes if you hit the ball on the bat and not the sweet spot, you can feel the bat sort of vibrate. So those vibrational modes are very similar to waveforms, if you will. And so these are different bending modes. And so you notice that this hockey stick can vibrate. You normally can't see it because it's vibrating at such a high frequency, you don't see that, but you can feel those vibrations. And so these are different modes of vibrations that hockey stick go into. Okay, and so again, real objects vibrate, they oscillate, and those oscillations can play an important role in how that thing behaves. Now there's some other ones. Let's see, here's one for a tennis racket. And so when a tennis racket hits a ball, oftentimes you'll see that that racket can also vibrate in your hand if you hit it outside of the sweet spot. There's a tremendous number of things for you to be able to look at. What I'd like to do is give you a few minutes to just look at something that you think is interesting, look at the animation, maybe read a little bit about it, and then what I'd ask you to do is to take this link that I'm going to send you and just add to it a comment. What simulation did you find interesting? What I'd ask is that you send a link to what that was, and then also briefly describe what you found there. Okay. Okay, so link for wave simulation. Find one thing you think is interesting, attach a link and a brief description of what it's showing. And again, folks, we're about 9:16. We go till 9:29 or so. So this is the last thing I was going to have you look at for today. And so take a few minutes, find something that you think is interesting, send us a link there, and then we can pack up for the day. Give her a go. Lots of things to be able to look at.